Hello, fellow warriors. Here we are with news from the website prostatewarriors.com.
Thanks for having me. I'm really excited to dig into all this today.
Yeah, we've got a lot. Today we are looking at a cancer that is so intelligent it can literally, well, it can sense when it's being starved of hormones.
Right.
And it responds by building its own private microscopic cholesterol factory just to keep itself alive.
Yeah, it's wild.
So we are unpacking a massive stack of updates today on how we treat advanced prostate cancer.
And it really is a profound shift in the biology of how we view this disease. I mean, for decades, oncology was kind of this game of brute force.
Yeah, like hitting it with a sledgehammer.
Exactly. Just, poison it and hope the cancer dies before the patient does. But now it is a game of molecular chess. The tumor constantly rewires its own survival mechanisms.
Which is terrifying, honestly.
It is. But the research we are diving into today shows that we are finally learning how to anticipate its next move, to corner it.
And to make sense of this chess match, we had a very specific game plan for this deep dive. We're going to start right on the front lines.
Right, the clinical trials.
Yeah, looking at actual trials happening right now with human patients, specifically cancer vaccines and cellular therapies.
Which is huge.
It is. And then, for the second half, we're going to head into the lab to explore those mind-bending metabolic escapes I just mentioned. And how we can trap the tumor.
I think it's the perfect logical flow for this. The clinical trials give us the tools we are deploying today, right? While the preclinical research, it kind of exposes the tumor as vulnerabilities for the therapies of tomorrow.
Okay, so let's jump right into the clinical trials, starting with vaccines. Conceptually, I mean, a cancer vaccine feels like the holy grail, right?
Oh, absolutely.
Because you aren't just poisoning the body, you are teaching the patient's own immune system to, recognize and hunt the cancer on its own. And the first one on our radar is the pTVG-HP DNA vaccine, which just had some long-term follow-up data come out from a phase 2 trial.
Yeah, so this trial focused on a very specific group of men. These were 99 patients who had already undergone definitive primary treatment.
Like surgery or radiation?
Exactly. But their cancer was coming back, so their PSA was rising, doubling in less than 12 months, actually.
Had no visible tumors.
Right. There were no visible tumors on a standard CT or a bone scan. It's what we call PSA recurrent, non-metastatic prostate cancer.
So the cancer is definitely there, and it's growing, but it's microscopic.
Exactly. Micrometastatic disease.
So over a 2-year period, these men received either the pTVG-HP vaccine combined with a protein called GM-CSF, or they just got the GM-CSF alone as a control group.
Right.
And I want to pause on GM-CSF for a second. That is essentially a molecular flare gun, isn't it? It signals white blood cells to swarm a specific area.
That is a great way to put it.
Yeah.
The GM-CSF stands for granulocyte macrophage colony stimulating factor.
That's a mouthful.
It really is. But basically, it stimulates the bone marrow to produce more immune cells. Yeah. And then it draws them to the site of the vaccine so they can actually, see the antigen we are introducing.
And the vaccine in this case is introducing a DNA plasmid, right?
Yes, carrying the code for PAP, which is a protein commonly found on prostate cancer cells.
But here is the massive paradox that immediately jumped out at me in the sources. The trial failed its primary endpoint.
It did.
The drug did not improve 2-year metastasis-free survival. If a drug fails to stop the spread at the 2-year mark, standard logic says it's a total failure, right?
Right, traditionally speaking.
Wait, the trial failed its primary endpoint of 2-year metastasis-free survival, but it still helped people live years longer. How does that work?
What's fascinating here is how this completely upends our traditional metrics for success.
Okay.
If you give a patient chemotherapy, you expect the tumor to physically shrink on a scan within a few months. And if it doesn't, well, the chemo failed. But vaccines do not work like chemical sledgehammers. They work by fundamentally altering the immune environment.
So they play a much longer game.
Much longer. When researchers look at the overall survival data years down the line, the median survival jumped from 8.6 years in the control group to an astonishing 13.4 years in the vaccine group.
Oh, wow. That is almost 5 additional years of life.
Yeah. In statistical terms, they reported a hazard ratio of 0.42.
Which means what exactly?
For those who don't read clinical trial data every day, that essentially means the patients receiving the vaccine had a 58% lower risk of dying during the follow-up period.
That is incredible.
It really is. What this tells us is that while the vaccine might not have eradicated every single micrometastatic cell quickly enough to prevent a recurrence on a 2-year scan, It trained the immune system to keep those rogue cells in check over the course of a decade.
So it created like a hostile environment.
Exactly. It slowed the disease down to a crawl.
That is wild. It really forces a conversation about how we design trials in the future. I mean, we might be throwing away effective immunotherapies just because we are judging them on a chemotherapy timeline.
Definitely. And this raises an important question about customization, too.
Oh, right.
Because the pTVG-HP vaccine uses a standard off-the-shelf antigen. But what if we could make a vaccine that is entirely unique to the specific mutations inside an individual patient's body?
Which brings us perfectly to the next trial happening at Mount Sinai. This is a phase 1 trial for a vaccine called PGV-001.
Yes.
And I was thinking about this. If the first vaccine is basically handing the immune system a generic sketch of a criminal,
Right.
like saying, hey, be on the lookout for a guy in a ski mask,
Sure.
then PGV-001 is something else entirely. It's like a highly bespoke, personalized, wanted poster.
The manufacturing process for this is a total marvel. I mean, after a patient undergoes surgery to remove their prostate,
Yeah.
the researchers actually take that physical tumor tissue and sequence its genetic code. They are looking for the unique mutations that cause that specific man's cancer.
Wow. And once they find those mutations, they create a multi-peptide vaccine tailored to that exact molecular fingerprint.
Right.
And then they combine it with a cytokine called CDX301 to, boost the immune response.
Yeah. And the critical step here is how they select those peptides. They look for mutation fragments that have the highest probability of binding to the patient's own MHC molecules.
MHC molecule.
Yeah. Think of MHC molecules as little display windows on the surface of a cell.
Okay, I can picture that.
The vaccine needs to ensure that the unique cancer fragments are placed perfectly in those display windows. That way, the passing T cells, the immune system's assassins, can clearly see them and memorize the target.
Oh, that makes total sense. And the timing of this intervention is brilliant, too. They are giving this to men who have 0 clinically detectable tumors post-surgery. But these are guys who are at a massive risk of the cancer returning. Like, the baseline requires a persistent PSA of at least 0.2 or a Decipher risk score of at least 30%.
Yes.
And a Decipher report, just as a quick reminder for anyone listening, is a genomic test that looks at the biology of the tumor to forecast how aggressively it might return.
Right. Because you want to deploy this weapon when the disease burden is microscopic.
Makes sense.
If you wait until a patient has, say, bone metastases, the tumor is large enough to secrete chemicals that actively suppress the immune system.
So you strike early.
You strike early. By doing that, the immune system has the numerical advantage and a highly detailed map of the enemy.
So upgrading the intelligence is step 1. But if vaccines are the intelligence pointing out the target, the next step is ensuring our immune system soldiers have the sheer energy and numbers to actually win the fight.
Yes, exactly.
Okay, let's unpack this. Because we are moving from vaccines into cellular therapies, our second group of clinical trials today.
Yeah.
And we have to start with Sipuleucel T.
Sipuleucel T is foundational. I mean, 15 years ago, it became the first cellular immunotherapy to show an overall survival benefit in metastatic castration-resistant prostate cancer.
It proved the concept actually works.
And it did.
But, I mean, the survival benefit was pretty modest, right? Around 4 extra months.
Yeah, that's right.
So the new phase 1 trial at Washington University is trying to radically boost those numbers by combining Sipuleucel T with an experimental drug called N803, also known as Anktiva.
And to understand why this combination is so potent, you have to look at their distinct roles in the body.
Okay.
Sipuleucel T involves taking a patient's own antigen-presented cells out of their blood, exposing them to a prostate cancer protein in a lab so they learn what to attack, and then infusing them back into the patient.
So it's the teacher.
Yes, it is a teacher.
And N803 is the fuel. From what I understand in the research, N803 is a superagonist for a cytokine called IL-15.
That's right.
And usually our bodies produce native IL-15 to keep our CD8 positive T cells and natural killer cells alive and fighting.
Yeah.
But native IL-15 has a terribly short half-life, right? Like, the body clears it away rapidly to prevent the immune system from going into overdrive and attacking healthy tissue.
Exactly. The body's natural safety brakes kick in too early. So the cancer survives because the immune response just runs out of gas.
I see.
But N803 is molecularly engineered to resist being cleared away. It mimics IL-15, but it stays in the system much, much longer.
Oh, wow.
Yeah, take a transient, fleeting immune response and turns it into a prolonged, aggressive pressure cooker. It literally forces the killer T cells to multiply rapidly and stay highly active.
So Sipuleucel T gives the soldiers the target, and N803 gives them endless rations and adrenaline to keep fighting.
Pretty much.
That is a brutal combination. But you mentioned the body's natural safety brakes just now.
Yeah.
Tumors are notorious for hijacking those brakes to protect themselves, aren't they? Which leads us to perhaps the most futuristic cellular therapy on our list today, CRG-150.
Oh, this one is amazing.
This is currently entering a phase 1/2 trial.
CRG-150 feels like science fiction, honestly, but it is happening right now. It is an autologous, CRISPR-edited cell therapy targeting the very cells that tumors use as a shield.
The regulatory T cells, right? Or Tregs.
Exactly, Tregs.
Because in a normal, healthy body, Tregs are the peacekeepers. They calm the immune system down so you don't develop autoimmune diseases.
Right.
But prostate tumors physically pull these Tregs into the tumor microenvironment and wrap themselves in a protective blanket of them, effectively turning the peacekeepers into bouncers that keep the killer T cells out.
That's exactly what happens. And the traditional way we deal with this in cell therapies, like CAR-T therapies for blood cancers, is incredibly harsh.
Oh yeah, it's brutal.
We usually give the patient high-dose lymphodepleting chemotherapy to literally wipe out their existing immune system, including those protective Tregs, just to make room for the new engineered cells.
And that is absolute hell on a patient's quality of life. The nausea, the risk of lethal infections.
Very tough on them.
But the protocol for this phase 1/2 trial of CRG-150 explicitly states there is no planned lymphodepleting chemotherapy prior to the infusion.
Which is a revolutionary step for patient safety.
Yeah.
And the reason they can skip the chemo is because of what they are doing with CRISPR gene editing.
Okay, lay it on me.
They extract the patient's cells and use CRISPR to knock out a specific protein called steroid receptor coactivator 3, or SRC3, inside those Tregs.
I really want to understand the how here. Like, we aren't just killing the Tregs. How does sniping this one single protein, SRC3, change the game so much that we don't even need chemo?
So SRC3 operates like a master switch inside the Treg that controls the release of suppressive chemicals, like TGF-beta.
Okay.
When the CRISPR edit disrupts SRC3, it fundamentally breaks that internal signaling cascade. The Treg loses its ability to secrete suppressive chemicals.
Wow.
But it goes further than that. The preclinical data shows that breaking this switch causes immunity.
Oh, mutiny!
Yeah, the edited cell actually flips its behavior and starts secreting inflammatory signals instead.
Oh, you're kidding?
Nope. You are taking the tumor's most loyal bouncers, reprogramming their genetic code, and sending them back in as Trojan horses to stimulate a local attack.
That is just brilliant. We are basically hacking the tumor's own defense grid.
It is stunning science.
Yeah.
But, we must maintain our clinical skepticism. It is early days.
Fair enough.
The researchers have to prove that these CRISPR-edited cells can survive the infusion, physically traffic their way into the dense tissue of a prostate tumor, and execute this mutiny effectively enough to shrink the cancer.
Right. So we've covered the clinical front lines: vaccines, supercharged T cells, and CRISPR-edited Trojan horses.
Yeah.
But what happens when the cancer just, sidesteps the immune system entirely? Like, what happens when a patient is taking powerful hormone therapies to starve the tumor and the cancer just figures out a back door?
It happens all too often.
Yeah. So for the second half of the deep dive, we are heading into the lab to look at metabolic warfare.
And this is where the sheer evolutionary drive of prostate cancer becomes terrifying. Prostate cancer cells are fundamentally addicted to androgens, like testosterone.
Right.
So our primary systemic treatment is to cut off that fuel supply, using chemical castration or by using advanced drugs like enzalutamide to block the androgen receptor directly.
Here's where it gets really interesting, because the cancer doesn't just passively starve to death.
No, it doesn't.
A recent preclinical study out of Weill Cornell Medicine looked at what happens when these cells are deprived of androgens, and they discovered the tumor literally rewires its basic nutrient metabolism.
Yeah.
Specifically, it starts hijacking two standard amino acids from the patient's diet, isoleucine and valine.
Right. Isoleucine and valine are essential amino acids. They are the building blocks of the proteins we eat every day.
Okay.
When a healthy cell breaks them down, it's just standard metabolism. But when an androgen-starved prostate cancer cell breaks them down, it heavily accumulates a byproduct called propionyl-CoA.
Propionyl-CoA.
Exactly. And this molecule is the key to the tumor's escape hatch.
The mechanics of this blew my mind when I was reading it. The researchers focused on a protein called SREBP2.
Yes.
I picture SREBP2 like a smart thermostat in your house, but instead of regulating temperature, it regulates cholesterol production in the cell.
It's a good analogy.
So if cholesterol gets too high, the thermostat clicks off. If it drops, it clicks on.
Right.
But this propionyl-CoA byproduct acts like molecular superglue. It chemically bonds to the thermostat, a process called propionylation, and permanently breaks it, locking it in the on position.
The regulatory feedback loop is completely destroyed.
Wow.
The cancer cell begins churning out massive, unchecked quantities of cholesterol, hoarding it inside the tumor microenvironment, regardless of how much is already there.
Which raises the obvious question, why does a prostate tumor want to hoard cholesterol? It's not trying to clog its own arteries.
No, it wants cholesterol because cholesterol is the base chemical precursor for all steroid hormones.
Oh.
The tumor realizes it isn't getting testosterone from the bloodstream anymore because of the patient's medication.
Right.
So it uses this broken thermostat and the resulting mountain of cholesterol to build its own localized factory. It synthesizes its own private supply of androgens right there in the tissue, completely bypassing the enzalutamide.
It's like a bootlegger during Prohibition.
Yes, exactly.
We shut down the main supply chain, so the tumor just sets up a speakeasy in the basement and distills its own fuel right under our noses.
That's a perfect way to look at it.
That is incredibly dark, but fascinating. Now, my immediate thought, and I guarantee this is the thought of any patient listening right now, is about diet.
I know where you're going with this.
Right, because isoleucine and valine are in chicken,
Yeah.
fish, dairy, eggs. Should a patient on enzalutamide just immediately go on a severe diet and stop eating protein to starve the bootlegger?
No.
Okay.
That is the most dangerous conclusion a patient could draw from this, and the researchers are explicitly warning against it. Do not make drastic dietary changes based on this lab data.
But if those amino acids are fueling the escape route, why not just cut them out?
Because you aren't just starving the tumor, you are starving the patient.
Oh, I see.
Restricting essential amino acids without intense, supervised medical intervention leads to muscle wasting and a lethal condition called cancer cachexia.
Oh, wow.
Yeah, the patient's immune system would collapse, and they would lose the physical resilience required to tolerate their life-saving therapies.
So the cure would literally be worse than the disease.
Precisely. The mice in the lab saw slowed tumor growth when these amino acids were restricted, but,
Yeah.
Mice living in sterile cages are not humans fighting complex systemic diseases.
Right.
We need highly controlled clinical trials to figure out if we can safely target the enzymes that break down these amino acids rather than just withholding food from the patient.
Yeah. We want to bomb the speakeasy, not starve the entire city.
Exactly.
And that concept of precision metabolic targeting brings us to our final piece of preclinical research. Because if the cancer can escape by hijacking proteins, it turns out it can also escape by hijacking fats.
Yes.
And this involves an enzyme called SCD1.
SCD1 stands for steroyl-CoA desaturase 1. To understand why this matters, you have to look at the physical structure of a cell. Cells are encased in lipid membranes, right?
Yeah.
SCD1 is an enzyme that takes stiff, rigid saturated fats and converts them into flexible, monounsaturated fats.
Okay, so saturated fats are like a stick of butter at room temperature, solid and stiff.
Right.
And monounsaturated fats are like olive oil, fluid and dynamic.
Exactly. When we hit a prostate cancer cell with a drug like enzalutamide, the cell undergoes massive stress.
Makes sense.
To survive that stress, divide, and spread, it requires a highly fluid, adaptable cell membrane. It also relies on those fluid fats to activate crucial internal survival signals.
Okay.
So, as an adaptation to the drug, the tumor becomes violently dependent on SCD1 to keep the olive oil flowing.
So the tumor leans all its weight onto this lipid metabolism pathway. And the researchers realized that if the tumor is leaning all its weight on that one pillar, well, that's exactly the pillar we should kick out. So they tested a combination therapy, hitting the tumor with enzalutamide to block the hormones, while simultaneously hitting it with an SCD1 inhibitor called aramchol.
Yes.
And what caught my eye is that aramchol isn't even a cancer drug, is it?
No, it is actually a drug currently in phase 3 clinical trials for severe liver disease called NANESH.
Oh, wow.
This is the beauty of drug repurposing. Because it's already in late-stage trials for another disease, we already have a mountain of human safety data.
Which dramatically accelerates how fast it could potentially reach cancer patients.
Exactly.
So they took this liver drug and paired it with enzalutamide, and they tested it against patient-derived VCAP-C cells in the lab.
Yeah.
And I want to pause on VCAP cells because they are notoriously nasty. They feature things like ARV7 splice variants and TMPRSS2-ERG fusions.
Very nasty.
Just to clarify for our listeners, ARV7 essentially means the androgen receptor is physically missing the docking station where drugs like enzalutamide normally attach. Like, it's a break and lock. And TMPRSS2-ERG means two entirely different genes have literally crashed together to create an uncontrollable cancer-driving engine.
They chose VCAP cells deliberately to test this combo against the most aggressive, treatment-resistant nightmare scenario they could find.
And the results were stunning. When they hit these resistant cells with both aramshal and enzalutamide at the same time, it caused a 3- to 4-fold increase in cancer cell death compared to using enzalutamide alone.
This is a textbook demonstration of synthetic lethality.
Break that down for me. Synthetic lethality.
Synthetic lethality is a scenario where a cell can survive defect A and it can survive defect B. But if you introduce both defects at the exact same time, the cell instantly dies.
Oh, I see.
The enzalutamide suppresses the main growth signal. The cancer tries to pivot to its lipid escape hatch to survive the stress, but the aramshal has already slammed that hatch shut.
Wow.
The cell's membrane loses its integrity, the stress becomes insurmountable, and the cancer cell suffers a catastrophic collapse.
It is literally nowhere left to run.
If we connect this to the bigger picture, you can see the overarching narrative of modern prostate cancer research. We are moving away from linear treatments and moving toward a coordinated, multi-front war.
Yeah, you can really see that.
On the immunological front, we are designing highly bespoke, customized vaccines like pTVG-HP and unleashing CRISPR-reprogrammed cells that refuse to be suppressed.
It's incredible.
And on the metabolic front, we are mapping the tumor's escape routes, whether it's hijacking amino acids to build a local cholesterol factory or relying on SCD1 to keep its cell membranes fluid.
Right.
And we are pre-deploying therapies to block those specific exits.
So what does this all mean? As we look across this entire landscape today, tumors are clearly not just static masses of bad tissue.
No, not at all.
They're deeply reactive, living ecosystems that dynamically rewire their own biology to survive the exact drugs we throw at them.
That's the reality of it.
Which leads to a wildly provocative thought. If we know that giving drug A will predictably force the tumor to build an escape route using pathway B, could the future of oncology rely on artificial intelligence?
Oh, absolutely.
Like, could AI analyze a patient's tumor and predict its next specific metabolic escape route before the cancer even has a chance to mutate?
Yeah.
Because then we wouldn't just be reacting to the disease, we would be preemptively cornering it, locking the doors before the tumor even realizes it's trapped.
That is the ultimate checkmate. I mean, the tumor thinks it is adapting, but we have already laid the trap based on its predictable biology.
Right.
And based on the incredible science we've reviewed today, we are finally learning how to see 3 moves ahead.
A huge thank you to the brilliant researchers pushing these boundaries, and an even bigger thank you to the patients participating in these clinical trials. Your courage is writing the blueprint for tomorrow. Stay strong and fight on.